The 1950s provided a wealth of experience to the Soviet armed forces regarding the application of surface-to-air missiles. While revolutionary, these systems faced a myriad of shortcomings, most notably their inflexible nature. This was problematic, considering the lack of SHORAD present at the time. The highly mobile warfare the USSR had grown to know throughout the Second World War demanded air defense that could maneuver with conventional formations, and missiles of the era could not meet this requirement. To cope with the modern battlefield, what the Soviet Army needed was an air defense weapon that could operate with autonomy across great distances in variable terrain, integrated at the divisional level. Initially, the 2K-12 satisfied these demands, which resulted in it becoming an organic element within tank divisions. The 2K-11 would supplement this capability by providing Army-level air defense. As these formations covered less distance relative to their size, the reduced mobility of the aforementioned weapons was acceptable. While armies and tank divisions were largely satisfied with their respective air defense weapons, the backbone of the Soviet military system, the motorized rifle division, was left with little more than anti-aircraft artillery supported by short-range missiles. At that time, medium-range missile systems did not have nearly enough mobility to keep up with these formations. To fill this gap, radically new technology was required. At this time, the United States had reached a similar conclusion, which resulted in the development of the Mauler, the requirements for which were drafted in 1956. The Mauler was conceptually well ahead of its time, harmonizing fire control, detection, and the missiles themselves on a tracked chassis was truly revolutionary. The system was to be delivered by 1963 with an expected production volume of 538 vehicles and 17,180 missiles. As is known, this did not transpire as expected. The requirements for the program were exceedingly optimistic. This was especially apparent when inspecting the missiles, which were to be functional out to 10 kilometers with a speed exceeding Mach 3.2 and capable of withstanding 30G maneuvers. These expectations were gradually reduced as the system began to fall increasingly behind schedule, resulting in the program being abandoned 2 years after its expected date of introduction. Many European militaries, including the USSR, would attempt to realize the idea of the ill-fated Mauler in the following years, to varying degrees of success. The Soviet military issued proposals for an affordable, simplistic, short to medium-range air defense weapon in 1958. The system that would trace its lineage back to this concept, dubbed the OSA, or WASP for its sting, would be the only one to get close. Order of the Central Committee of the CPSU and the USSR Council of Ministers No. 138-61, issued February 9, 1959, would officially commence the development of what would eventually become the OSA. A year later, in 1960, another order would be issued, containing the first requirements expected of the program. The complex was to be capable of engaging aircraft, exploiting low altitude to avoid long-range SAM systems, flying at speeds of up to 500 meters per second. These specifications were ideal for the protection of motorized rifle formations on the march. Because this system had to accompany motorized rifles no matter the location, great emphasis was placed on its amphibious capabilities. Studies conducted at this time determined that at optimal offensive pace, motorized rifle divisions would have to contend with minor water obstacles every 20 kilometers, medium water obstacles every 60 kilometers, and major water obstacles every 300. This meant one major crossing each day and many minor crossings. If a unit's air defense had to rely entirely on bridging equipment, it would massively reduce the autonomy of these formations. It was also exceedingly important that the vehicle be able to detect targets while in motion and engage them quickly from short stops. At this time, it was known as the ellipse. This continued the geometric designations present within Soviet SAM systems. Furthermore, it had to carry enough missiles to engage 2 to 3 targets and operate advanced computer systems allowing for somewhat autonomous operation, and be mounted on a chassis capable of being transported by an AN-12 or IL-76 with a full combat load of fuel and ammunition. The missiles fired by this vehicle had to have a hit probability around 70% against a MiG-19 sized target at a range of 6 kilometers, an altitude of 3 kilometers, and a slant range of 3 kilometers. The variant of this system intended for the Army, which is the subject of this video, was to have its development supervised by Ni-20, who would also spearhead its radar. MMZ was instructed to design the chassis and the launcher, while Factory Number 82 and Factory Number 118 GKAT would produce its missiles. Ni-131 GCRE was given the task of creating motors and gyroscopes for the project alongside Ni-125 GKOT, which was given the task of developing the missile's solid-fuel rocket. The first year of development was spent working on a preliminary design, while the second was dedicated to testing the numerous prototype missiles provided by the aforementioned organizations. From 1962 to 1963, manufacturing test batches of prototype missiles was to be conducted with the intention of preparing for state trials. In an order prepared by the Central Committee of the CPSU and the USSR Council of Ministers, the system was re-designated OSA. This was issued October 27th of 1960, with the intention of motivating those working on the project. This motivation was desperately needed, as in this same document the requirements for the program were raised significantly. The primary difference from the original proposal was the slant range being increased to 10 kilometers. This delayed development by a quarter, but this was expected. This order also provided insight into how the system's chassis was chosen. It was considered ideal to employ a vehicle that was already slated to enter service within motorized rifle divisions to increase parts compatibility and reduce the need for specialized training. Proposals from across the USSR were inspected, with the ZIL 153, Object 1015B, Object 560, and Object 560U being considered. Gorky won the competition with their BTR-60, as it was the most reliable, mobile, and inexpensive. These qualities actually worked against the vehicle, and in 1961 the concept was dismissed due to its inability to support the OSA's weight. ZIL, who was considered a reasonable second choice by the team, also pulled out for these reasons. While Object 1015B of the Kutaisi automobile plant would be rejected by the Ministry of Defense for its inability to conform to the requirements of the program it was initially designed to satisfy, a modification, designated 1040, co-developed by the Moscow Military Academy of Armored and Mechanized Forces, became the ideal platform to mount the OSA. The team tasked with developing the OSA were under the impression that much of the program's technical research and development would be conducted off the back of subsystems created for the 2K11. This included 30 transistors and semiconductor diodes. Initially, all that had to be developed was a unique operational amplifier, comparable to the RU-50, a vacuum tube in use across the USSR. This amplifier served as the foundation for the development of the OSA's onboard computer, which originally contained 200 of these amplifiers, but was eventually reduced to just 60. The specifications that accompanied the designation OSA proved challenging to actualize, as there was no existing technology within the USSR that could reasonably facilitate such low-altitude engagement, coupled with its unreasonably short period to detect and engage targets. What made matters worse was that these features had to be condensed into a platform that could cross rivers, board transport aircraft, and keep up with a motorized rifle division. High-output multifunction antennas would be required. VM Taranovsky and his team at NE-20 got to work developing a brand new phased array radar. This halted the development of the OSA for quite some time due to the complexity of the task. In 1958, the US faced similar issues when developing the Typhon, which demanded a radar capable of fire control and target illumination, known as SPG-59. The cost, high energy consumption, and weight of this radar led to it being cancelled in 1963. The prospect of installing a phased array radar on the Mauler encountered similar complications. Solutions too advanced for the time were abandoned over the course of the year to avoid delays. To make matters worse, KB-82, responsible for creating the 9M33 missile, were running into similar issues. KB-82 was an experienced organization. They were one of the first plants to produce the S-25, which led to multiple improvements being introduced by its staff. They pursued many projects of their own, none of which went anywhere, and just before beginning work on the 9M33 had been involved in the S-125's development. While the missile was not yet known as 9M33, I'm going to use that title because it's easier than saying the missile over and over and over again, so I hope that you can understand. The 9M33 had equally ambitious requirements. It had to weigh no more than 60 kilograms and be no longer than 2.65 meters. High accuracy was required, and so semi-active radar homing was proposed. KB-82 considered a myriad of weight reduction methods, after which they concluded throughout preliminary analysis that the guidance system, fuse, and power source should be under 14 kilograms. This left 40 kilograms for propulsion and steering. This did not pan out, as expected. The aforementioned elements turned out to weigh 27 kilograms, nearly double the previously established limit. Concerns also arose regarding the propulsion mechanism, as the propellant designed by KB-2 was a 31.3 kilogram charge mixed with solid fuel that provided 10% less energy than what was used to create the 40 kilogram estimate. To solve this issue, KB-82 attempted to create its own engine using experience they had gained trying to produce the V625's propulsion mechanism. This unfortunately went nowhere. Continuing this trend, development on the chassis was beginning to stall. Object 1040 exceeded all previously established weight requirements and could only carry 3.5 tons. This was 1 ton less than the most optimistic predictions for the final weight of all subsystems, and half of the pessimistic assumptions, which placed OSA at 6 tons. To somewhat reduce the vehicle's weight, its defensive weapon, a machine gun, was removed, and its 220 horsepower engine was swapped with a lighter 180 horsepower alternative. Indeed, OSA was a battle for every kilogram, so much so that by September of 1962, NE-20, so fed up with these issues, began offering 200 ruble rewards for each kilogram saved, and 100 rubles for every 100 grams. Engineers working on the project often took 2 shifts or worked overtime to cash in on these bonuses. The need to cast 200 pieces employed throughout the design in magnesium created financial concerns as the molds would shrink, which was problematic as these were molds for prototypes so experimental that no coherent manufacturing process had been created for them. Teams from various aviation plants lent their services to NE-20, but even with this increase in manpower, there was no way to produce enough molds fast enough to keep up with development. The kilogram bounty would last until February of 1968. These issues prompted the Council of Ministers for Military-Industrial Affairs to revise the overly optimistic requirements. The ambitious application of semi-automatic radar homing was replaced with radio command guidance. The range of the missile was reduced to 7.7 kilometers, and its weight was increased to 65 kilograms. The warhead was also modified, now weighing 10.7 kilograms. By 1962, NE-20, in cooperation with Plant 368, had finalized 7 onboard equipment sets. While this was a major breakthrough, it was 60 short of what was originally promised. Furthermore, the plans for prototype missiles to be fired by the third quarter of 1962 also fell through, as the radar had yet to be produced. It was only by the end of 1963 that 4 launches could transpire, only one of which was successful. On February 8th of 1964, with deadlines on the horizon, the Council made the development staff aware of the fact that moving forward, they would be held responsible for all future delays. A commission was organized to assist the team, which was headed by experts in the field. Notably A.A. Rosplatin of KB-1 and P.D. Grushin of OKB-2, with the goal of identifying features that were in reality technological dead ends. Poor management over the program's resources and abundant feature creep were noted as the primary issues plaguing the OSA. After initial considerations to remove all relevant organizations from the project, offering the OSA to more qualified OKBs, the Commission analyzed foreign excursions to create a similar platform, notably the Mahler, Seacat, Rapier, and Kratal. Afterwards, it was concluded that a 65-kilogram missile was impossible, considering the technology that was available internationally. As a result, the weight was amended to 115 kilograms. The missile's warhead also needed a mass increase to around 14.5 kilograms. This was due to concerns that radio command guidance would result in near misses, which was not unfounded, and with the existing warhead, it would be impossible to damage a target if this transpired. Finally, the missile was designated 9M33, and was to operate a 31-kilogram payload. To reduce the diameter of the weapon, this payload included the warhead, fuse, electronics, and power source. It would house an M20 computer and operate a dual-thrust solid-propellant rocket engine, allowing for the missile to reach speeds of 550 meters per second. A 2-stage variant was rejected as it would increase the 9M33's weight by 3 kilograms and its length by 100 millimeters. A ramjet was also considered, but this would have cost the team 500 millimeters and 13 kilograms. 9M33 would be capable of maintaining supersonic speed for up to 8 kilometers. Its wings were made to freely rotate on a bearing relative to the longitudinal axis of the missile. This solution was chosen as the missile had to overcome lateral overloads of 25 Gs, while still being stable and controllable. Canards were chosen for the aforementioned reasons, but this meant that the air deflected by them would affect the wings. One proposal to combat this was the installation of ailerons on the wings alongside additional servo motors to allow for differential rudder deflection to smooth out the issue. But this would have abundant weight-related consequences. 9M33 was such a compact missile that no room existed to install additional servo motors. It was for this reason that the previously described method was employed. Interestingly, a similar solution was used in the Magic missile. 9M33 had 5 compartments, 3 of which were dedicated to the missile's control equipment, allowing for the electronics, fuse, power source, and warhead to be isolated. This made servicing the missile exceedingly simple, which was done once a year on-site where the missiles were stored. 9M33 being made up of aluminum alloys such as VAD1 and V96C3, as well as KVK26 and KVK42 steel, was difficult to manufacture. Rotary extrusion and explosive forming were required due to their application. The missile was momentarily worked on by both KB-82 and OKB-2, but by September of 1964, development of 9M33 was transferred entirely to OKB-2. State testing was scheduled for Q2 of 1967. By March of 1965, 4 prototype 9M33s had been produced, each weighing 117 kilograms. These missiles used mock electronics to simulate the real weight of the missile. On March 27, 1965, a prototype missile was released by an aircraft. This was done as Object 1040 had not yet been finalized. The missile traveled 12 kilometers. This success led to another missile being prepared. 2 seconds after the prototype detached from the aircraft, its motor exploded. On April 8th, the last two missiles were dropped, and they both demonstrated the success displayed during the first test. These follow-up experiments were conducted with the intention of determining how the missile would function with its wings locked. After the success experienced in April, it was time to test the missile from the ground, which had mixed results. On the first launch, the missile's status was to be recorded on an oscilloscope. The individuals monitoring this oscilloscope noted relatively normal readings. About 20 seconds after launch, they were urgently informed that the missile had exploded. This claim was dismissed as the oscilloscope's readings showed perfect uninterrupted flight. It was only until 20 minutes later that another attendee of the test came in to note that the missile smoldering remains now rest not far from the launcher. Despite this, the oscilloscope believed otherwise. After 30 minutes of confusion, it was determined that the missile's motor had exploded with such haste that barely any acceleration occurred, meaning its sensors fell to the ground undamaged and continued to transmit without issue. By summer of 1965, 9M33's teething issues had been resolved and Object 1040 was ready. This meant that OSA could finally be unified and tested as one system. 4 complete OSA prototypes were produced. 2 were sent to conduct cross-country mobility testing to determine its general performance and reliability when crossing water obstacles, which involved a combined 10 hours of swimming. The system's 0.7-ton excess resulted in unacceptably poor road speed, and a mean time before failure of 10,000 kilometers instead of the required 15,000. To solve the weight issues, the vehicle's steel construction was replaced with aluminum. Some present at the test proposed removing the spare parts stored aboard the chassis. These concerns did not stop 2 launches from occurring in October of the following year. Issues arose when the missile deviated heavily from its expected flight path. In some cases, this was so bad that the missile failed to align with the radar entirely. This was determined to be an issue with the rail, which was reinforced on site. After this modification, the missile flew as intended. Alarmed by this, Grushin sent individuals down to the Kutaisi automobile plant where the vehicle's chief designer was located. His work was constructively critiqued, which was not taken well. He made it clear that the plant had only agreed to work on this project to bring some prestige to its name, and they had not the manpower nor material to realize its requirements. When questioned about the lack of workers present at the facility, he explained that today football is on TV and everyone took the day off to watch the torpedoes. It was decided there that the plant would be cut from the OSA project. As the missile was determined to be functional, the development team suggested mounting it on an MTLB. This was rejected. Though issues were once again beginning to mount, the OSA remained an unusually fickle program. Serial production was slated to begin by October 11, 1967, but this was impossible as the vehicle was overweight. On top of this concern, after trials were conducted against a radio-controlled IL-28 in 1967, and firing trials on the move in 1968, it was stated by the commission that the team had failed. The vehicle did not feature a 360-degree engagement capability. It could not effectively engage low-flying targets. Guidance errors were abundant. The missile was horribly unreliable. It took far too long to be made operational and could not meet range, speed, or buoyancy requirements. Further trials were suspended, and to the devastated staff who had given so much to this project, it looked like the OSA was doomed to fail. But somehow, despite all that was stacked against them, they were determined to finish what they had started. After a heated argument and another meeting, the team was given a maximum of 2 years to finish the OSA. If they failed, the project would officially be cancelled, and their careers would be in jeopardy. Immediately, a new chassis had to be designed. As the Bryansk automobile plant still had stakes in the program, they got to work creating the BAZ 5937, which would become the OSA, the BAZ 5938, its maintenance vehicle, and BAZ 5939, its reloading vehicle. These vehicles employed a modified version of the UTD-20 found in the BMP-1 and 2, which was designated 5D-20B-300. The chassis was equipped with state-of-the-art technology such as night vision devices for the crew, R124 intercom, R123 very high-frequency radios, and an automatic fire suppression system. Each variant was also equipped with a TNPO-170 observation device used when crossing water obstacles. To get the OSA into production, after a fierce internal debate, Ni-20 decided to omit the stabilization system required for firing on the move, in favor of short stops, which still proved satisfactory. Detecting targets and tracking them on the move was retained, and so all that had to be done was for the crew to put the vehicle at rest long enough to guide the missile to its target. A second channel was also introduced so that the OSA could guide 2 missiles at once to a single target. There is a very strange myth that the OSA could guide 1 missile to 2 targets, but this was physically impossible, as the radars did not allow for this. Following these revisions, the project resumed with fresh enthusiasm. It took only a few months to completely alter the system's equipment. Notable introductions included a TV sight, improved navigation equipment, and improved radar structure to reduce vibrations experienced while the vehicle was in motion, and more ergonomic switchology. After a year and some change, the OSA no longer resembled its prior iterations and had effectively become an entirely new complex. The 9A33 combat vehicle, as it was designated, mounted a coherent pulse centimeter band horizontally stabilized radar, which rotated at a speed of 33 revolutions per minute. With each rotation, its beam would switch from one of 3 positions. With a power of 250 kilowatts, receiver sensitivity around 10 to the negative 13th watts, beam width in azimuth of 1 degree, and in elevation from 4 to 19 degrees, it could detect targets out to 40 kilometers at an altitude of 5 kilometers. If the target's altitude was 50 meters above the ground, it could be detected out to 27 kilometers. Upon detecting a target, the vehicle would stop, the track station transmitter was engaged, and the radar would begin following the aircraft automatically. Tracking was conducted by a centimeter band 200 kilowatt radar with a sensitivity around 2 to the negative 13th watts, and a beam width of 1 degree. This system could follow targets at a range of 23 kilometers at an altitude of 5 kilometers. This was reduced to 14 kilometers at an altitude of 50 meters. The target's data would be received by the OSA's computer, which generated information to feed to 1 or 2 missiles fired at the threat. When operating in heavy ECM environments, the target could be tracked through its angular coordinates by aiming the TV sight towards the aircraft. To facilitate the guidance of 2 missiles, the OSA made use of 2 sets of wide and medium beam antennas. When firing at low-flying aircraft, the OSA employed the Gorka method of interception, which involved the missile approaching an aircraft from above. This was done to avoid the 9M33's proximity fuse, which was programmed by the altitude of the target being triggered by the ground, and to reduce guidance errors. In March 1970, the 9A33B was ready for factory trials, and in July, a state commission had already been prepared to observe the system within the Kiev military district. Unfortunately, when firing at LA-17 drones, the OSA struggled to predict their altitude. Due to the tracking radar locking in place when engaging low-flying targets, the crew could not achieve this estimate themselves. For this reason, optical tracking was used, but this did not solve all of the OSA's low-altitude engagement issues. As was mentioned previously, the fuse was programmed by the target's altitude. This caused the missile to prematurely detonate when passing over objects at a similar height, such as trees and buildings. This was resolved with time, but such complications made this set of trials unusually difficult. It was also found that despite the vehicle's equipment being improved substantially, OSA could not be prepared for operation within the required 2 minutes specified by the Commission. A factory in Leningrad was contacted and tasked with installing vacuum tubes within the offending elements to increase the speed that they could be warmed up. While tests of the new chassis lag behind the previously determined schedule, its eventual evaluation in Moscow was significantly better than the disaster experienced years prior. Simultaneously, as all of these events transpired, the State Commission struggled with an unusually difficult task. That was figuring out how to integrate the OSA and how units operating the system would be organized, and most importantly, their staffing structure. This was problematic as the OSA was a uniquely complicated piece of equipment, demanding a uniquely qualified crew. For this reason, the expected workload of a single OSA was that of an entire battery of long-range SAM systems. Further issues arose when determining how OSA operators would be trained, as longer service was needed to master such a weapon. The concept of placing 2 officers in one vehicle was floated. One would be a targeting officer and the other would be a guidance officer, but this was determined to be a waste of resources. Despite this, according to studies conducted by the Ministry of Defense to analyze the efficacy of a single officer controlling the system, the workload of an OSA crew commander was akin to that of a platoon commander. This was unacceptable, and so a warrant officer was chosen as a reasonable compromise to fill the place of the proposed guidance officer. The Commission concluded its work in February of 1971 and scheduled a final meeting in Moscow with those developing the OSA to discuss the project's enduring issues. It was decided that all the complications remaining with the chassis could be resolved in time by the Ministry of Defense, and that the OSA was to be accepted for service on October 4th. While its name remained unchanged, the platform that was accepted in October looked very different than what was proposed a decade earlier. The OSA was capable of engaging targets flying at speeds of 300 meters per second at altitudes between 200 and 5,000 meters, at a maximum range of 9 kilometers. Targets flying at speeds of up to 420 meters per second could be engaged out to 7.1 kilometers. The maximum lead angle was 4 kilometers. The missile weighed 128 kilograms and had a length of 3,158 millimeters. It was determined that the possibility of hitting an F-4C with a single missile at altitudes above 100 meters was, in the worst possible conditions, 42%, and in the most favorable, 85%. It had a maximum road speed of 80 kilometers and could cross water obstacles at speeds between 7 to 10. The vehicle was accompanied by the 9T-217B, which carried 8 missiles, the 9V-120, which conducted maintenance and repairs, a mobile testing station known as 9V-242 for verifying the functionality of the OSA's onboard equipment, and the 9F-914 calibration vehicle designed to resolve any issues detected by the former. Serial production of the 9M33 missile was carried out at plant number 32 in Kirov. 9A33B was manufactured at the Izhevsk electromechanical plant. The first OSA was delivered in September 1970. 3 more would be produced in 1971 and another 15 in 1972. By 1973, 3 batteries had been formed. The moment the OSA was accepted into service, modernizations were proposed to increase its range and ease of operation. One issue that was noted during the Moscow trials was the lack of rear visibility present on its chassis. The solution to this issue was expedited by the planned unveiling of the OSA through 12 units at the Red Square Parade scheduled for the 7th of November 1975. During training that preceded the occasion, 9A-33Bs struggled to stay in formation, as their operators could not easily view what was behind them, and to their sides. 8 of the 12 vehicles present received a unique window configuration to resolve the issue. This inconsistency did not go unnoticed by foreign analysts in attendance. The first official modernization to the OSA began development in 1971. The system's computer was to be improved as to increase the accuracy of the coordinates it generated. This would in theory allow for the engagement of aircraft traveling at speeds of 500 meters per second. An external coherence mode was also introduced to provide further redundancy against electronic countermeasures. The various markings throughout the vehicle's interior to denote the function of its switches were also revised for increased readability in low-light conditions. This variant, dubbed OSA-A, was to be completed by 1974, but as was typical with anything OSA-related, this deadline was overly optimistic. Ustinov, during a routine visitation to various manufacturers of high-profile military equipment, came to inspect the production of the OSA at the Izveshk mechanical plant. Ustinov stated that the rate in which OSAs were rolling off the assembly line was unsatisfactory and that production had to be increased substantially. After finishing the tour and seeing multiple 9A-33Bs in their finalized state, Ustinov exclaimed that it should be without issue possible to increase the ammunition capacity of the vehicle by a factor of 2. Those who worked at the factory in earshot of this remark quickly objected to the insinuation and described all of the reasons this was impossible. Ustinov's rejection of these arguments, as was remembered by those present that day, was rather humorous. He turned to VP Yefremov and stated, "That is your problem, see that it is resolved." Grushin was contacted and informed of Ustinov's overconfidence. Remembering prior threats to his credibility leveled by Ustinov in the wake of delays experienced in the 60s, Grushin understood that this was serious and that work was to begin immediately. Studies on how 8 missiles could be accommodated on the existing chassis revealed that 6 containerized missiles were easily supported. Ustinov was contacted and approved the design by comparing the situation to getting a tuft of wool from a mangy sheep. This new model, designated OSA-K, was approved for development on February 7, 1973. Ustinov was so excited about this prospect that he asked to be credited as an assistant to the project, as he had proposed the idea. It was decided that work on OSA-A and OSA-K could reasonably be consolidated into one project, which led to the title OSA-AK. A new development that accompanied this designation was the ability to engage targets at a minimum altitude of 27 meters, which was done by improving the missile's fuse. This new missile was designated 9M33M2. It did not differ from 9M33. The only notable differences outside of the improved fuse was the introduction of folding wings to accommodate the containerization. Factory tests of OSA-AK transpired between 1973 and 1974, which involved trials of the new BAZ 5937 chassis. State trials of the system began in September of 1974 and continued until February of 1975. No issues were encountered throughout this process, and the OSA-AK was accepted into service. Work to further modernize this variant of the OSA began immediately in November of that year. The primary issue still present, reducing the efficacy of the vehicle, was its inability to accurately target helicopters. This proved difficult as it involved alterations to the missile and the radar. A new guidance method was needed, an improved computer was required to facilitate this, and additional modes for the fuse had to be introduced. This new guidance method involved the radar only providing range data. The target would be tracked primarily through the TV optic. The missile would fly above the line of sight before descending on the target at a 25-degree angle. This solution could only be employed by missiles operating the improved radio proximity fuse, which were designated 9M33M3. Factory tests of this new complex were conducted in 1977. In September 1979, state trials began, which were muddled by a lack of radio-controlled helicopters to test the new capability on. To solve this unique complication, a real helicopter was situated on top of a wooden tower which mimicked the minimum engagement height. Wood was used to not interfere with the radar. The helicopter used for this test was an Mi-2 recently removed from service. It was flown onto the tower by a pilot who planned to observe the test. Unfortunately, due to the terrain present at the range, the actual height of the tower was around 10 meters. To accommodate this, the fuse was adjusted alongside certain elements of the guidance method, after which the missile impacted the target with extreme precision. The tower was destroyed and its remains caught fire. This upset the deputy commander who supervised the range. This did not deter the OSA's development staff from celebrating. 2 railcars arrived with additional timber so that a second tower could be constructed. It met an identical fate to the tower that came before it, resulting in the team being banned from creating any more fire hazards. In preparation for the Zapad 81 exercise, 4 towers were constructed for the OSA to engage. Sources disagree on if the helicopters chosen for the exercise were taken from models actively in service, or if they primarily employed helicopters soon to be decommissioned, like Mi-4 number 7, pictured here. It is unknown if this specific helicopter was used for OSA testing, as there is no mention of it being used for this purpose. The older helicopters attracted less than favorable attention from the Mi-8 and Mi-24 pilots, who did not seriously believe that they were going to be flown, and referenced them as unusable dumps. The reason that it cannot be verified if this is a OSA target was because 20 decommissioned helicopters were also sent to Zapad 81 in preparation for various firing trials. In 1980, the OSA once again had to be improved, which slightly delayed the already complete OSA AKM from entering service. In this case, the present threat was UAVs and cruise missiles, and the vehicle's inability to detect them. The only visible difference between these upgraded models is the integration of a switch labeled Engage Cruise Missiles. This switch, when activated, slightly modified the guidance method and fuse to better engage small targets. OSA AKM would enter service that year and was praised for its ability to engage targets practically on the ground out to 6.5 kilometers. Minor modifications were introduced to improve this capability, which increased the possibility of destroying such a target with a single missile. Additional modernizations that entered service alongside the OSA AKM included increased automation in regards to data exchange between elements within a battery, which allowed OSA batteries to interface with the Maneuver Automated Command and Control System, which I have a video on. The introduction of diversion devices to thwart anti-radiation missiles, which could be activated to provide a target for incoming arms while 9A33 shuttered their targeting radars. This specific bit of information was gleaned from statements made by veterans on certain forums and other locations, and so it is difficult to know if this was actually standard. Other SAM systems employed similar methods in exercises which did not actually have any standardization, but there are claims that a standardized diversion device may have entered service with the OSA AKM, but as it stands, it's impossible to know. OSA AKM entered service in anti-aircraft missile regiments within motorized rifle divisions, which consisted of 5 batteries in a command post. A battery contained 4 systems and a battery command post. In total, a regiment contained 20 9A33 BM3 combat vehicles and 80 missiles. When equipped with the earlier OSA AK, 120 missiles were present. The regiment's control post operated a PU-12M, which transmitted data obtained by the accompanying P-19 search radar to the regiment's subunits. It was possible to integrate P-19 search radars into each battery, and this was oftentimes engaged in preparation for tactical exercises. In peacetime, the location of a regiment's command post was located near the formation's garrison, taking into account terrain features that may diminish the P-19's detection range from the west and southwest. Batteries were pre-positioned to defend surrounding objects of importance. For example, the 30th Guards Motorized Rifle Division situated its air defense regiment 500 meters north of the Slop airfield. In the event of hostilities, the immediate task of the regiment was to protect communications facilities, the 30th Guards Motorized Rifle Division, and the airfield, with priority being given to the garrison. Concrete fighting positions often housed 9A-33s to prepare them for this task. Each battery command post was defended by additional manpads. Each command post operated its own observation post for the anti-aircraft team accompanying them. To conserve fuel in peacetime, the vehicles operated by each battery were supplied power by civilian infrastructure when in a defensive posture. This ensured that they could operate their radars without actually running the vehicles. The battery was surrounded with 2 rows of barbed wire and covered with camouflage nets. False fighting positions were erected to deceive enemy aircraft into striking positions in which no vehicles were located. 9A-33s were accompanied by 4 manpads in their fighting positions. OSA veterans stated that if it was difficult to track or engage helicopters, making especially effective use of terrain masking, these manpads were their final line of defense. 2 RPG-16s were available in each dugout, but if the situation was dire enough that these actually had to be employed, it was likely already too late for the crew. Smoke generators, thermal decoys, and other implements to deceive the enemy were also present. Once the battery was severed from civilian power, 5-ton diesel tanks were provided to ensure 24 hours of independent operation. The battery's support assets included a cook and signaler operating an R-115 radio station. There are some sources which state that P-18 and P-40 radars were also present. There is a common misconception that the 2S-6 Tunguska was considered superior to the OSA and because of this was slated to replace the system. This could not be farther from the truth. The Tunguska was momentarily considered a redundant weapon system as the OSA AK already featured a superior engagement range against fixed-wing threats. It was for this reason that the Tunguska was marketed as a solution to the helicopter threat, as this was something the OSA of the time could not accomplish. Interestingly, this problem was solved by the OSA AKM, which was introduced 2 years before the 2S-6 passed state trials at the Donguz test range. OSAs and Tunguskas did operate together. Veterans had complaints regarding the Tunguska's ability to catch up with them as they maneuvered with motorized rifle units. This was in some regards problematic, as they did indeed possess the greater helicopter engagement capability, and so if they were not in range by the time this threat arrived, the OSA would have to deal with it themselves. When conducting combat operations as a part of a motorized rifle division, the regimental headquarters is comprised of a regimental commander, deputy commander, chief of staff, and deputy for armament and logistics. The regiment's chief of reconnaissance and chief of communications are accompanied by a senior encoder and his staff. The regiment's support assets include a medical section, motorized supply service, a fuel supply element, and a meteorologist. It is stated that a battery's most important capability is reconnaissance. This is understandable as continuous reconnaissance allows the unit to detect threats before they arrive, identify friendly aircraft, and study the terrain to determine likely avenues of approach. Passive radar reconnaissance is assisted by active reconnaissance from each 9A-33 crew through the TV optic. The battery's command post will establish its own air observation post using its reconnaissance staff, who will be provided with optics to engage this task. This should, in theory, allow for targets to be detected from 8 to 25 kilometers. These elements become increasingly important in situations where the enemy is employing heavy electronic warfare and the detection capabilities of the battery's radar has been significantly reduced. It should be noted that if each battery is employing a search radar, they can exchange information between each command post. This is important because if one battery is being jammed, it is possible for even the regimental command post to transmit data to each battery based on what its search radar is detecting. The number of targets a battery can track is dependent on the number of target channels available to the formation. This is one of the primary figures employed by the battery's commander to determine its fire capabilities, which is described as the number of airborne threats a battery can destroy. This is derived by analyzing the number of missiles available, functional target channels, and the dimensions of the engagement zone. The quality of each channel, the possibility of destroying each target fired upon, and the readiness of the formation to respond to a threat are also factored into this conclusion. For an attack lasting 30 minutes in difficult meteorological conditions at night, assuming the battery's crews are well trained, with one 9A33 missing a target channel due to a malfunction, and each crew being allocated 4 missiles to expend 1 per target, it is possible to determine that this particular battery can destroy 2 aircraft, while effectively repelling the attack. The math used to reach this conclusion is displayed on screen. It is possible for an entire battery to deploy within 35 to 50 seconds, depending on the skill of the crew, and break down into march order within 15 to 30. The speed in which one 9A33 can shift its focus to a new target after rendering a threat inoperable can be accomplished by an exceptional crew within 40 seconds and a subpar crew within 120. There is a very strange misconception that has been floating around the OSA for quite some time, which is that it requires unusually high clearances to pass under bridges and through tunnels. This is not the case. The minimum clearance required by the 9A33 is around 4 meters, which is pretty standard. The battery marches in a single column with the formations, PU-12, and maintenance vehicles in the rear or in front. Some photos will show them in the rear, some photos will show them in the front. It's kind of impossible to determine what is ideal. The distance between each vehicle should be no less than 25 meters, and ideally spaced out to 50 when possible. When marching in anticipation of an attack, vehicles will keep a minimum distance of 200 meters and may even operate 800 meters from one another. The battery should at all times be prepared to make short stops to engage the enemy. This is done by rapidly pulling off the road before acquiring a target and firing. When advancing to the line of contact during an offensive maneuver, and when pursuing the enemy, the battery moves in combat formation. This is considered the ideal posture to defend against air attacks. Batteries will break their vehicles into pairs, which will be positioned 3 kilometers from one another. Pairs of 9A33s will be spaced apart by 200 meters. This ensures an ideal engagement envelope by overlapping 9A33's maximum range. The formation is usually positioned 1.5 to 3 kilometers behind the formation. 1.5 is ideal, but 3 kilometers can be done when necessary. Reloading vehicles are positioned 500 meters from 9A33 pairs. It is most common for a battery to be attached to each motorized rifle regiment in a division. This is known as Advanced Detachment Operation. When covering a motorized rifle unit crossing a water obstacle, the batteries will position themselves 2 kilometers from the river. Batteries will then conduct crossings in pairs after the unit they are covering has secured the opposite bank. During a prolonged engagement, it is possible that a battery will be assigned to prepare an anti-aircraft ambush. This can be done from multiple predetermined points or by assigning pairs of vehicles to act as roving security elements. Roving units will quickly reposition from predetermined points over the course of a defensive operation. As the formation they are covering advances, vehicles will bound in pairs to ensure overlapping coverage. Every 3 to 4 hours, the battery will halt and inspect the operability of its equipment using the accompanying diagnostics vehicles. This is also where the battery will refuel, eat, and rest for up to 2 hours. When marching at night, shorter rests of around 1 hour can be engaged with greater consistency. These are done without breaking formation. It is possible that the battery will make use of Bemetil and stimulants to ensure longer marches, fewer rests, and enhanced mental acuity. In situations with especially high electronic interference, usually as a result of targeted jamming from an aircraft or other installations, 9A33s are permitted to engage counter-jamming only when it is impossible to track the enemy through any other means. It's unknown what is meant by counter-jamming, and I have not been able to find any information regarding specialized systems within the OSA to engage this. It's highly likely that what this means is something similar to what was employed across many Soviet radars at the time, which was a mechanism to counteract specific common jamming types, especially noise jamming denying range information, which still allows for azimuth and elevation to be determined. This was defeated by a circuit which, based on the rate of change and signal received, can recognize an attack, will store the last known range and closure before jamming occurred, after which it can extrapolate from the data where the target is and determine a somewhat accurate range. It's also possible that this is telling the system to employ data linked range, and that's why it can only be employed in certain circumstances, which I will describe in a moment, but to me it is unknown what that means. If anyone has any ideas as to what this could imply, I would be very, very interested in hearing your statements on the matter. What is known and described across multiple manuals is the application of mixed targeting, where the vehicle switches between semi-automatic and automatic tracking modes. 9A33s will only switch on their counter jammers when firing at a target, and should avoid engaging this when tracking an aircraft. This is why I believe that it could very well be a range estimation system. When anti-radiation missiles are employed by the enemy, the target is to be tracked without emitting, or emitting in a significantly reduced fashion. This is done either through the TV optic, intermittent radar operation for only 2 revolutions, switching off the radar once the missile has reached a sufficient distance from the target, or switching off the radar immediately upon missile detonation. The TV optic may be assisted by quickly engaging the 9A33's tracking radar before immediately shutting it off to gather sufficient data about the target. If an aircraft is approaching the formation, the TV optic is usually the best option, and should be switched into its widest setting. These tactics proved rather effective in Syria, as Israeli electronic warfare and SEAD operations struggled to reduce their efficacy. It is stated in some secondary sources that every jamming tool present at the time was tried, and failed to prevent the OSAs from operating and threatening their pilots. This confirmed statements made after 9A33s were tested against Soviet electronic warfare capabilities at the Ember range. Those who partook in these trials stated that the OSA's resistance to jamming was unrivaled when compared to any other missile in service at the time.